Graphs and Iterative Processing. In graph-like data models on page 49 we discussed using graphs for modeling data and using graph query languages to traverse the edges and vertices in a graph. The discussion in Chapter 2 was focused around alt-style use, quickly executing queries to find a small number of vertices matching certain criteria. It is also interesting to look at graphs in a batch processing context, where the goal is to perform some kind of offline processing or analysis on an entire graph. This need often arises in machine learning applications such as recommendation engines or in ranking systems. For example, one of the most famous graph analysis algorithms is PageRank, which tries to estimate the popularity of a web page based on what other web pages link to it. It is used as part of the formula that determines the order in which web search engines present their results. Dataflow engines like Spark, Flink, and Tez see materialization of intermediate state on page 419 typically arrange the operators in a job as a directed acyclic graph DAG. This is not the same as graph processing. In dataflow engines, the flow of data from one operator to another is structured as a graph, while the data itself typically consists of relational style tuples. In graph processing, the data itself has the form of a graph. Another unfortunate naming confusion. Many graph algorithms are expressed by traversing one edge at a time, joining one vertex with an adjacent vertex in order to propagate some information, and repeating until some condition is met, for example, until there are no more edges to follow, or until some metric converges. We saw an example in Figure 2-6, which made a list of all the locations in North America contained in a database by repeatedly following edges indicating which location is within which other location. This kind of algorithm is called a transitive closure. It is possible to store a graph in a distributed file system in files containing lists of vertices and edges, but this idea of repeating until done cannot be expressed in plain MapReduce, since it only performs a single pass over the data. This kind of algorithm is thus often implemented in an iterative style. An external scheduler runs a batch process to calculate one step of the algorithm. When the batch process completes, the scheduler checks whether it has finished based on the completion condition. For example, there are no more edges to follow, or the change compared to the last iteration is below some threshold. If it has not yet finished, the scheduler goes back to step 1 and runs another round of the batch process. This approach works, but implementing it with MapReduce is often very inefficient, because MapReduce does not account for the iterative nature of the algorithm. It will always read the entire input dataset and produce a completely new output dataset, even if only a small part of the graph has changed compared to the last iteration. As an optimization for batch processing graphs, the bulk synchronous parallel BSB model of computation has become popular. Among others, it is implemented by Apache Giraffe, Spark's GraphX API, and Flink's Jelly API. It is also known as the Progel model, as Google's Progel paper popularized this approach for processing graphs. Recall that in MapReduce, mappers conceptually send a message to a particular call of the reducer because the framework collects together all the mapper outputs with the same key. A similar idea is behind Progel. One vertex can send a message to another vertex, and typically those messages are sent along the edges in a graph. In each iteration, a function is called for each vertex, passing it all the messages that were sent to it, much like a call to the reducer. The difference from MapReduce is that in the Progel model, a vertex remembers its state in memory from one iteration to the next, so the function only needs to process new incoming messages. If no messages are being sent in some part of the graph, no work needs to be done. It's a bit similar to the Acker model. See Distributed Acker Frameworks on page 138. If you think of each vertex as an actor, except that vertex state and messages between vertices are fault-tolerant and durable, and communication proceeds in fixed rounds. At every iteration, the framework delivers all messages sent in the previous iteration. Actors normally have no such timing guarantee. The fact that vertices can only communicate by message passing, not by querying each other directly, helps improve the performance of Progel jobs, since messages can be batched and there is less waiting for communication. The only waiting is between iterations, since the Progel model guarantees that all messages sent in one iteration are delivered in the next iteration. The prior iteration must completely finish, and all of its messages must be copied over the network before the next one can start. Even though the underlying network may drop, duplicate, or arbitrarily delay messages, see Unreliable Networks on page 277. Progel implementations guarantee that messages are processed exactly once at their destination vertex in the following iteration. Like MapReduce, The framework transparently recovers from faults in order to simplify the programming model for algorithms on top of PRGL. This fault tolerance is achieved by periodically checkpointing the state of all vertices at the end of an iteration, i.e. writing their full state to durable storage. If a node fails and its in-memory state is lost, the simplest solution is to roll back the entire graph computation to the last checkpoint and restart the computation. If the algorithm is deterministic and messages are logged, it is also possible to selectively recover only the partition that was lost, like we previously discussed for data flow engines. A vertex does not need to know on which physical machine it is executing when it sends messages to other vertices. It simply sends them to a vertex ID. It is up to the framework to partition the graph, i.e. to decide which vertex runs on which machine, and how to route messages over the network so that they end up in the right place. Because the programming model deals with just one vertex at a time, sometimes called thinking like a vertex, the framework may partition the graph in arbitrary ways. Ideally, it would be partitioned such that vertices are collocated on the same machine if they need to communicate a lot. However, finding such an optimized partitioning is hard in practice. The graph is often simply partitioned by an arbitrarily assigned vertex ID, making no attempt to group related vertices together. As a result, graph algorithms often have a lot of cross-machine communication overhead, and the intermediate state messages sent between nodes is often bigger than the original graph. The overhead of sending messages over the network can significantly slow down distributed graph algorithms. For this reason, if your graph can fit in memory on a single computer, it's quite likely that a single machine, maybe even single-threaded algorithm, will outperform a distributed batch process. Even if the graph is bigger than memory, it can fit on the disks of a single computer. Single machine processing using a framework such as GraphQI is a viable option. If the graph is too big to fit on a single machine, a distributed approach such as PRGL is unavoidable. Efficiently parallelizing graph algorithms is an area of ongoing research. High-level APIs and languages. Over the years since MapReduce first became popular, the execution engines for distributed batch processing have matured. By now, the infrastructure has become robust enough to store and process many petabytes of data on clusters of over 10,000 machines. As the problem of physically operating batch processes at such scale has been considered more or less solved, attention has turned to other areas: improving the programming model, improving the efficiency of processing, and broadening the set of problems that these technologies can solve. As discussed previously, higher-level languages and APIs such as Hive, Pig, Cascading, and Crunch became popular because programming MapReduce jobs by hand is quite laborious. As TES emerged, these high-level languages had the additional benefit of being able to move to the new dataflow execution engine without the need to rewrite job code. Bark and Flink also include their own high-level dataflow APIs, often taking inspiration from Flume Java. These dataflow APIs generally use relational-style building blocks to express a computation, joining datasets on the value of some field, grouping tuples by key, filtering by some condition, and aggregating tuples by counting, summing, or other functions. Internally, these operations are implemented using the various join and grouping algorithms that we discussed earlier in this chapter. Besides the obvious advantage of requiring less code, these high-level interfaces also allow interactive use, in which you write analysis code incrementally in a shell and run it frequently to observe what it is doing. This style of development is very helpful when exploring a dataset and experimenting with approaches for processing it. It is also reminiscent of the Unix philosophy, which we discussed in the Unix philosophy on page 394. Moreover, these high-level interfaces not only make the humans using the system more productive, but they also improve the job at execution efficiency at a machine level. The move toward declarative query languages an advantage of specifying joins as relational operators compared to spelling out the code that performs the join is that the framework can analyze the properties of the join inputs and automatically decide which of the aforementioned join algorithms would be most suitable for the task at hand. Hive, Spark, and Flink have cost-based query optimizers that can do this, and even change the order of joins so that the amount of intermediate state is minimized. The choice of join algorithm can make a big difference to the performance of a batch job, and it is nice not to have to understand and remember all the various join algorithms we discussed in this chapter. This is possible if joins are specified in a declarative way. The application simply states which joins are required, and the query optimizer decides how they can best be executed. We previously came across this idea in query languages for data on page 42. However, in other ways, MapReduce and its dataflow successors are very different from the fully declarative query model of SQL. MapReduce was built around the idea of function callbacks. For each record or group of records, a user-defined function, the mapper or reducer, is called, and that function is free to call arbitrary code in order to decide what to output. This approach has the advantage that you can draw upon a large ecosystem of existing libraries to do things like parsing, natural language analysis, image analysis, and running numerical or statistical algorithms. The freedom to easily run arbitrary code is what has long distinguished batch processing systems of MapReduce heritage from MPP databases. See comparing Hadoop to distributed databases on page 414. Although databases have facilities for writing user-defined functions, they are often cumbersome to use and not well integrated with the package managers and dependency management systems that are widely used in most programming languages such as Maven for Java, NPM for JavaScript, and RubyGems for Ruby. However, dataflow engines have found that there are also advantages to incorporating more declarative features in areas besides joins. For example, if a callback function contains only a simple filtering condition, or it just selects some fields from a record, then there is significant CPU overhead in calling the function on every record. If such simple filtering and mapping operations are expressed in a declarative way, the query optimizer can take advantage of column-oriented storage layouts. See column-oriented storage on page 95 and read only the required columns from disk. Hive, Spark data frames, and Impala also use vectorized execution. See memory bandwidth and vectorized processing on page 99, iterating over data in a tight inner loop that is friendly to CPU caches and avoiding function calls. Spark generates JVM bytecode and Impala uses LLVM to generate native code for these inner loops. By incorporating declarative aspects in their high-level APIs and having query optimizers that can take advantage of them during execution, batch processing frameworks begin to look more like MPP databases and can achieve comparable performance. At the same time, by having the extensibility of being able to run arbitrary code and read data in arbitrary formats, they retain their flexibility advantage. While the extensibility of being able to run arbitrary code is useful, there are also many common cases where standard processing patterns keep reoccurring, and so it is worth having reusable implementations of the common building blocks. Traditionally, MPP databases have served the needs of business intelligence analysts and business reporting, but that is just one among many domains in which batch processing is used. Another domain of increasing importance is statistical and numerical algorithms, which are needed for machine learning applications such as classification and recommendation systems. Reusable implementations are emerging. For example, Mahout implements various algorithms for machine learning on top of MapReduce, Spark, and Flink, while MADlib implements similar functionality inside a relational MPP database. Apache Hawk. Also useful are spatial algorithms such as k-nearest neighbors, which searches for items that are close to a given item in some multi-dimensional space, a kind of similarity search. Approximate search is also important for genome analysis algorithms, which need to find strings that are similar but not identical. Batch processing engines are being used for distributed execution of algorithms from an increasingly wide range of domains. As batch processing systems gain built-in functionality and high-level declarative operators, and as MPP databases become more programmable and flexible, the two are beginning to look more alike. In the end, they are all just systems for storing and processing data.